Okay, good morning everybody. Thank you for turning up here so early. It's a very early start today. Welcome to our talk on hard launching CSR Racing 2. I'm going to start with a little bit about what CSR Racing 2 is. So as you may have guessed, CSR Racing 2 is the sequel to CSR Racing 1. And CSR Racing 1 was released all the way back in June 2012. It's still played today and has had 190 million downloads to date. CSR 2 was soft launched to a number of territories in September 2015 and then hard launched worldwide June this year. Our game is a drag racing car collecting game which is supported on over 2,500 Android and iOS devices. And I'm now going to play a short video which demonstrates CSR 2. So throughout our game's development, our studio has focused on delivering one of the most visually ambitious titles, and to do this across as many different devices as possible. We started with an internal mission statement of trying to make a game that wows people, with the main goal of delivering AAA console visual quality. But what happens after release? Because after the game goes live, changing the underlying tech is a bit like trying to change the wheels on a moving car. And for this reason, most studios tend not to develop their visuals beyond launch. But to maintain our competitive advantage, we've had to be prepared to reinvent our visuals. And mobile games can be typically spend years in live ops, which we can ill afford to let our visuals stagnate over that time. So for that reason, we've been keen to try and adopt an approach that's more similar to desktop MMOs than traditional console DLC. So how do you change the wheels on a moving car? Or more like a couple of thousand moving cars, given the number of devices that we actually support. So over the next 40 minutes, we will show our approach to revisiting and improving existing tech. We'll show how we did this and and how we created pipelines that allow for innovation on new devices while maintaining the support on existing ones. So a little about who we are. I'm Liam Murphy, a senior graphics programmer at NaturalMotion Games. And I'll be doing the first half of our talk, which is mostly focused on the lighting pipeline changes that we've made since the game's release. And in the second half, I'll be handing over to my colleague Scott Harber, our lead technical artist. And Scott's going to be doing a talk talking about the evolution of our post-processing within CSR 2. And in case you're wondering why this talk is in Unite, CSR 2 was actually built inside Unity 4. The live build's currently on 4.7.2. We're also excited to announce here today that we're in the process of migrating to Unity 5. That's something worthy of its own talk, but that'll have to wait to another time. And in this section, I'm going to give a brief overview of our key rendering decisions in place at hard launch. You can find out more information on this from the GDC presentation that I gave earlier this year, and I'll provide a link to that later. So first off, we're a forward-rendered title, and while this is not necessarily a given on mobile, the bandwidth and memory limitations of the platform made this our preferred option. And a big part of achieving our photorealistic ambitions meant following the footsteps of the console world and adopting a physically based shading model. And so our game features a suite of completely bespoke car and environment Uber shaders. We use specular and diffuse cube maps to statically light almost everything in the game. and the use of parallax correction helped us achieve the appearance of motion reflections for when the car is in the race. And we use our own type of emulated HDR to give us realistic materials like car paint and glass, which are difficult to achieve in standard LDR rendering. Now, achieving realistic visuals at high frame rates on the top 80 devices at soft launch was a strong feat in itself. But amazingly, thanks to top-down art direction and a strong focus on low-end performance, we were able to up our device roster to 2,500. Since then, we've had new devices coming to the market, which have opened up new graphical headroom, and we're keen to utilize on that. And we've had the challenge of a regular release schedule, bringing content to our users while trying to keep in performance budgets. So as you've seen from the demo, the game was already beautiful at hard launch and has received huge praise for its visuals. But after hard launch, we had a strong desire to keep the momentum going visually. And we went about this in two different ways. Firstly, we focused on VFX bolt-on improvements, which are targeted to devices that can afford it. And you'll see this well covered in Scott's part of the presentation. Secondly, we spent time reanalyzing our existing systems to see if we could make improvements. And with regard to that part, we started by analysing some of the weaknesses in the visuals that had been brought up a few times internally. Like how in dark environments, it seemed to be very difficult to get the cars not to look too dark. And we'd often resort to rebalancing all of the assets to get the brightness levels that made sense. But then we'd end up in situations where the cars wouldn't sit right in the scene. And it looked sort of a bit superimposed, really. And tyre balancing was particularly problematic. One of our biggest revelations, though, came towards all of these issues, came when we compared assets in the game engine with an offline renderer using real-world HDR captures. And we were looking at the reflections in the car, and which had a sort of pearlescent paint to it. And what we essentially saw was this. So in our engine, the reflections of a sort of pearlescent paint had a smooth, dark sort of look to them, seen here. But in the offline renderer, they had sort of bocky highlights with inside them. And after thinking about it, we'd realized we'd missed a big trick in our lighting pipeline. We found that we were baking our specular convolution with LDR inputs. What does this mean? Well, with our LDR inputs, the peak brightness is capped on your sharpest MIP 0. And when you blur, the signal gets dimmer and flatter. This means that very bright light sources bleed out in the blur very quickly. But with HDR inputs, the peak brightness carries deep into the blurriest MIPs, maintaining that intense brightness of real bright, bright lights that you see in the real world. So I realise I've used some fairly exotic terms here, and I thought I'd take this opportunity to clarify. So for those unfamiliar with the idea of specular convolution, I'm talking about the process of taking a crisp reflection and then calculating a discrete number of increasing blur levels to use for rough material support. Now, we use PMREMs in the game, and that's an abbreviation for pre-filtered mip-mapped radiance environment maps. And that's essentially, in our case, a cube map where the MIP chain has been replaced with progressively blurrier versions of the sharpest MIP. So back on topic, to understand our new changes, I'm going to outline our old 8-bit pipeline and the transition to the 32-bit convolution. So as mentioned earlier, for scalability reasons, CSR2 uses emulated HDR. And in seeing this in this image above, the technique works by taking a low-range color exposure, a high-range grayscale exposure, putting them through our lighting pipeline, and then using those results in the game to give us HDR-like visuals. The old 8-bit pipeline starts with 2 cube map renders like you've seen in the previous slide. We then put those through the convolve process to give us rough material support, and we use the tool AMD Modified Cube Map Gen for this. That tool outputs 3 different cube maps, 1 diffuse cube map and 2 different exposure specular PMREMs. We then feed those cube maps into a combining script inside Unity, resulting in a diffuse cube map with alpha encoding in the MIP level. And this is useful for a technique that I'll cover later. It also outputs a specular PMREM with the low range encoded in color and the high range encoded in alpha. In the new 32-bit pipeline, we add a new stage before the convolution step. Here we take two different exposures, combine them into one full 32-bit HDR cube map using a Photoshop feature. Now that 32-bit cube map can be then fed into our convolution tool, which will now properly preserve the energy held in the very bright lights across both the diffuse and the specular outputs. So going one step further, we've recently been able to strip away that quirky process of trying to simulate a 32-bit render from two 8-bit renders inside Unity 4 by rendering our cube maps with inside Unity 5, which properly supports HDR cube map renders. So with all that in mind, let's look at what the changes did for us. So what you're looking at here is a material matrix of our garage scene. On the horizontal axis, we have increasing material refractive index, and on the vertical axis, we have increasing smoothness. In this example, we've used cube maps which were baked within 32-bit sources instead of 8-bit ones. And the thing that's most noticeable here is the brightness increase in materials which are both highly reflective and very rough. So you've seen a material matrix of the difference the pipeline changes make, but why should you care? Well, the first reason is that the change has a real difference in the color tone of your diffuse cube maps, and here's a good few examples of that in action. So in this scene, we have two spheres. The left one showcases the diffuse convolved in 8-bit, and the right in 32-bit. Now, we found that the cars sat in the scene looked much better seated when using the warmer 32-bit cube map, despite the scene looking very cool. Now, this is quite counterintuitive, really, but it's actually happening because the vast majority of the energy within the scene is actually coming from the bright lights, the yellow street lamps, and not from the blue reflections on the environment or the sky. In this outdoors daylight scene, we knew that most of the light was actually coming from the sun and the sky. But the diffuse cube map convolved in 8 bits has already had the sun and the sky's brightness tone mapped downwards, and has already had the shadowed canyons tone mapped upwards. So hence you can see the orange visible in the left sphere, the lower hemisphere of that. And thanks to this change, we saw our car setting better in that environment as well. So the next reason you should care about convolving cube maps in 32-bit is because it alters the shape of them in your diffuse cube maps. So this change can help you evidence the presence of strong directional lights within your scene. Here's a good example of that in action. So in this scene, you can see how the 8-bit convolved diffuse cube map on the left has a sort of gradual top-down gradient within inside it. Now this has happened because the brightness of the sun towards the horizon has had its brightness truncated to the cloud surrounding it. This doesn't happen with the 32-bit version you can see on the right, which clearly indicates where the sun is in the scene. Another finding we had was the understanding that the samples from the diffuse cube map and the fully blurred specular should be approximately the same. So in the above image, this shows a transition from the rough diffuse material through to the rough specular one. In our 8-bit convolved cube maps, there's a noticeable change in the intensity levels. But truth be told, this is actually because originally we'd artificially boosted our diffuse to compensate for the dark specular, rough specular we were seeing. After moving to the 32-bit convolution, we were able to drop the diffuse boosting and not only have bright, rough diffuse, but also to have bright, rough specular as well. This has had particularly big effects on certain materials in scenes with low lighting. Here's a good example of that in action. So the tyre in this low lighting scene has details that pop out of it that just weren't even visible before in the 8-bit convolution. And this is what the change does to our W motor Lycan Hypersport. And to our Mini Cooper S. And best of all, in low lighting scenes, this is what it does for our Nissan GT-R Premium's engine. It's like someone switched the light on there. But that is literally, that's the difference it makes. As you can see from the before and afters, we were very pleased with the results. But these changes do come with one drawback, and that's that they contribute to an increase in sample aliasing. So to demonstrate, here's our Chevrolet Corvette Z06. The changes here are going to be somewhat difficult to see, but because of the contrast on the projector, but you should be able to make them out still. Here we're using the garage lighting setup, which has been convolved in 8 bits. I've chosen the moderately low resolution of the iPhone 5S here to highlight the issue, which is mainly noticeable in very detailed areas of the car, such as the wheel or the grille. So in this next slide, which is convolved in 32-bit, you can see the switch. Now, the aliasing differences don't appear to be too noticeable in the still image, but they can detract from the boost of realism that the improved lighting setup gives us when the camera's in motion. So in this pipeline change, we've needed no codes yet so far. So why has sampling aliasing increased? Well, prior to any iteration, the MIP0 should look exactly the same on both 8-bit and 32-bit setups, but that's where the similarities stop. As we move through the MIP chain, the higher energy signal of the 32-bit setup will propagate through. This will lead to steeper gradients in the cube map, and then cause an increase in contrast throughout your MIP chain. That will increase the frequency of detail within your blurrier MIPs, and all this will lead to an increase in sample aliasing. So what are some of the things that we've done to address sample aliasing? Well, as mentioned earlier, our image-based lighting setup requires that we replace distance fall-off blur with our specular cube maps MIP chain with the convolved blur instead. So this means that the natural MIP fall-off won't work properly. And to combat this, we use a technique called MIP bias. And this technique works by emulating natural MIP selection and picking from blurrier specular levels than usual for samples that would suffer from sample aliasing. And by the way, this is the algorithm that requires the MIP level, which is why we encode the MIP level into the diffuse cube maps alpha, something I mentioned earlier on in the talk. So here's an example of MIP bias in action. You can see that there's a noticeable drop in sample aliasing here. But when we try to use the same technique on our new 32-bit convolved cube maps, we see that while it's useful, it's lost some of its power. And this is happening because the MIP chain now has a much higher contrast throughout it now, and MIP bias works best when the signal flattens quickly through the MIPs. So what else have we done? Well, another thing I recommend to do is to work with your artists to author lighting which works within the limitations of your system and to avoid filling your scene with high frequency, high contrast details. And we've also added a technique we've named HR dimming. And this works by dimming down high range details on fragments which are picking from texels being MIP biased. So going back to the previous slide, here's the result of us using MIP bias with our 32-bit cube maps. And here is the result of the HR dimming algorithm, which targets problem aliasing areas. So the difference is most noticeable, though, when you're comparing between when you're using no mitigations and techniques at all, such as this one. So while on the topic of sample aliasing, one thing we realized while we were investigating the lighting pipeline was that while we were limited to 512 pixel specular cube maps, there was no reason that we couldn't render the original source in, say, a much larger resolutions of 2K and then downsample it back to 512 prior to convolution. Here's an example of the change that makes. So all of a sudden, details like the fire extinguisher become instantly recognizable. And you can also see that the missing lines in the windows pop back into view. And you'd also, it's easy to think that those details aren't going to be noticeable in the reflections, but convex geometry can really magnify the reflections, making it very noticeable indeed. So this is the difference that it makes on our Ventador SV's windows. So I'll wrap up my part of the talk now with some conclusions. Firstly, when your art ambitions are all about photorealism, it pays to get as much of your tech and processes to abide by PBR principles. And when you don't do this, your artist may be able to get the balanced look that they're after, but it will come at the cost of endless iterations and probably leave you with that sort of superimposed look that's very difficult to fix. Next, for maximum quality, it's worth trying to make the HDR support that you have as wide and as clean as possible in your rendering pipeline. Sometimes gaps in the support, which you wouldn't think matter, actually do. Assets used in the game can be generated or a product from a combination of steps at alpha time, build time, load time, run time. And when revisiting your rendering pipeline for improvements, it's worth looking at where in the pipeline those assets come from. Doing this sometimes results in the lifting of assumptions that you may have had on the limitations of quality. Now finally, game engines are a product of progressive work and feature add-ons. And it's easy to think that once you've completed one component, it won't need revisiting. But some of the biggest quality gains can be had by doing just that. Too often we'll have glossed over something in the original implementation or had requirements change so much over time that the original text no longer fit for purpose. Okay, well that's my part of the talk over. Here's some references of possible interest. I'll wrap up now with a special thanks to Michael and our car team for their contributions on what I've covered today. And I'll now hand you over to my colleague Scott Harber for his part of the talk. Thank you.
Oh. Hey everyone. Thanks for coming out, and more importantly, thanks for coming to us instead of the Unity roadmap meeting. Honestly, that means a lot. So now that we've covered all of the changes we've done to our lighting and specular pipeline, let's talk about the other thing, the post effects. So for a bit of context, this is what our game looked like when we soft launched it way back when in the midst of time in the turbulent year that was 2015. And we're doing some fancy stuff with shaders at this point, and to a lesser extent the world. Excuse me, but for the most part, it is just brute force polygons and texture work, just doing what you would expect on mobile, just cranked up to 11. And it looked good enough for the time, but good enough is never good enough. So if we compare it to how we hard launched it about 9 months later, it's moved on a little bit. Subjective issues of quality notwithstanding, I hope you can all see that the art style is significantly more ambitious now. And the reason that we can do that is because we're doing more with color biasing, we're doing more with full screen lens effects, we're drawing on the screen itself, and we're doing lens flares and all the rest of it. And the reason we can do all that is because during that 9-month period, we doubled down on our post effects. And there are reasons why we did this. The first one being, it is the ultimate polishing tool. In the games industry, and especially the mobile industry, there is that mentality that quality equals polygons. And that's true to an extent. That'll get you about 80% of the way to good. But post effects will get you the extra 20% and put you over the top. We've all seen movies or behind the scenes footage from movies where you see a bunch of guys in front of a green screen and then they draw the background behind them and it all looks a bit rubbish and a bit handheld. And then they paint the whole thing green and then suddenly, oh my God, it's filmic. We wanted to harness that kind of power, but on a mobile phone. Simple, right? Actually, yeah, kind of. Because the beauty of being a video game is that at any one time, your video game is going to have different use cases. You're not going to need all of your post effects all the time. So it becomes a very useful way of compartmentalizing your systems and optimizing them in quite a nice way. More info on that later. It's also a good art direction tool. Imagine the possibilities of being able to just take a screenshot from your game, giving it to your art director and letting them scribble all over it in Photoshop, and just having that be your visual target. We wanted that too. And from a logistical point of view, if you want to affect the maximum number of pixels on the screen with the minimal amount of dev time, resources, and let's face it, effort, it's a useful tool in that regard too. But it's not a perfect solution. It comes with its own challenges, especially in the field of mobile. The first one being, as Liam alluded, is that we support a lot of devices, as in 2,500 of them, 25 of which are iOS. But the number of the devices is less of a factor so much as the extent of the specs that we have to support. Without going into detail and showing you a whole bunch of graphs, it's the equivalent of trying to support 3 or 4 different console generations with the same data set. Imagine trying to hit many moving targets with a single bullet and you understand the problem. With regards to our game itself, we made the choice of being a forward-rendered game, which to an extent precludes the use of multiple render targets. So if we wanted to do a depth pass for depth of field or motion vectors for motion blur, it's probably a little rich for our blood at this point. Similarly, because we simulate our HDR, it precludes the use of HDR bloom buffers or anything like that. So I'm just going to rewind the whole thing a bit just to explain how post effects work, just to get an idea of the audience understanding. And the way we create a post effects shader, just like any other pipeline, is that we write a shader. And the shader just runs on every pixel on the screen. And concurrently, you have a script that sits on your camera that takes a render of the screen and sends it to the shader as a texture. So far, so standard. The downside of this approach is that it runs on every pixel on the screen. So if you've got a 16:9 device with a 1080p resolution, that means that you're going to be running your shader 2 million times per frame on 2 million pixels. And depending on the complexity of your shader, that gets expensive very quickly. And all things considered, that's your best case scenario because the modern devices go quite a way north of 1080p. And when that does happen, yes, it's true that sometimes the resolution will scale with the amount of GPU that they give you. But this isn't always the case. And when it is, it's not always enough. And when it is, it's never consistent between all devices. So we've got that whole issue of trying to hit multiple targets at once again. Neither of these problems are completely avoidable, but they can be mitigated. I've got 4 top tips for being able to do it. Top tip, the first, is to have some kind of a scalability pipeline. I'm not going to go into super details about this because I've done it in previous conferences before. Look me up. And what you want to be able to do is, instead of trying to support 2,000 devices, instead try and support like 3 or 4 quality levels, like your low spec and your mid spec and your high specs, for example, and then assign each device to them. And once you've done that, it determines how much post you can have on each device. Some may be able to do everything, some may be able to only do some of it, and some may be able to do none at all. Your mileage may vary on this, but anecdotally speaking, this is what we found with iOS devices. If your device is low spec, i.e. anything before 2012, don't even bother. Unless you're being really, really frugal with your shaders and your polygon counts, you're going to find that just the sheer cost of taking a render of the screen and putting it to a shader makes the whole thing prohibitive. Comparatively, any device after 2014, go for it. Anecdotally speaking, again, CSR2's post-effects pipeline, which I'm going to show in a minute, will run between 3 and 7 milliseconds on an iPhone 6, which at this point is 2-year-old hardware. So that gives an indication of how far of a leap you can make in that time frame and what the likes of iPad Pro or iPhone 7 are going to do. As for the middle children, this can vary quite wildly as consistency was less of a factor in these days. You'll find that in all those cases, you'll only be able to do a subset of what you can do on the high-spec devices, but the subset will vary. So you'll find some devices are GPU-bound, and that means you'll only be able to do some of your post, and some will be CPU-bound, and you can have pretty much all the post at the expense of draw calls, and so on. With regards to Android devices, they're not quite as evenly consistent as shown here, which is why I haven't listed them, but you kind of got to feel your own way around to make that work. Can't really help you with that, but best of luck to you. Top tip, the second. And this one's kind of taken the wind out of my sails a bit because the keynote kind of answered this one, but you want to do this in as few render passes as possible. As tempting as it would be to braid the image effects folder in Unity and just start stacking your favorite post effects onto the camera, the cost of it quickly becomes cumulative. Case in point, you've got your post effect shader, you've done your 2 million pixels, then you do another 2 million pixels to do motion blur, and then again for bloom, and then again for depth of field, and. The alternative is to try and do the whole thing in one mega post-effect shader of your own design and just use preprocessor directives to turn features on and off and shader keywords to turn features on and off as you need to. This isn't always a practical option though, because if you're doing something that's computationally expensive, doing that at full frame and full resolution can be prohibitive. In which case there are scenarios such as blooms and blurs where it's better off to do those as a separate render pass, but not to be too precious about the resolution. I mean, here is a very coarse example of what I'm talking about with regards to how you can scale things and still get the same results. But there's going to be more information on this later. So my fourth and final tip, and again, I alluded to this earlier in the introduction, is to choose your effects based on the content that you want to show. At any one time, your game is going to have different use cases because you're not always displaying the same content. Depending on the game you're making, you'll have very different results. But in the case of CSR2, there's only two use cases that we needed to support. The first one being the pre-race. And the idea behind this is that before the race starts, two cars rock up to the start line, and nothing happens until the player presses that throttle button, which, as far as exploits go, means that the player can just camp on this track indefinitely and scrutinize any aspect of it in extreme detail. So individual asset fidelity is paramount here. So the cars need to look amazing, everything in the world needs to look amazing. And in the case of post effects, individual pixel quality needs to be really high too. So, we're doing more with our lens effects. You can see we got the old J.J. Abrams lens flare going on that don't walk sign, and we've got a little sort of full screen halo rainbow effect in the bottom left corner there. And we've got animated lens effects because it's a wet weather environment, and we're doing things with height fog and depth and all the rest of it. Compare that to a race in motion, and individual pixel fidelity is much less of an issue because it's all about the sense of speed at this point. So motion blur suddenly becomes the most important thing in the world. And in the case of the lens effects, we start animating things to provide visual interest. And we're doing things like drawing the bloom on top of the motion blur to give the look of energy conservation, and we're turning up the VFX and all the rest of it. So far so theoretical. But let's see how this looks in practice. Let's build a shot from our game to show what I mean and how we approach this. So here is a naked shot from our game with no post effects on it at all. Now already, because our art team is just really that good, it's already looking kind of good. But kind of good doesn't get you on stage at Unite. So let's put a color grade on it. And the color grade, as you can obviously see, is really quite subtle. And it's subtle for reasons that are about art direction. Case in point, in our game, the car is the star. Being a mobile game, CSR2 is free, but the cars, the user has the option to pay for them and to pay for customization options. So they can choose their own paints, they can choose their own liveries, they can mix them up and create something very consistent. And they want to be able to see that consistency across all of our levels. So if we have one particular level where everything is washed blue, and you put a white car in there, the white car looks blue. Red cars look purple, and so on. So just for being able to appreciate the car in every place, while we do want to maintain color washes, because that's what next-gen things look like, we have to keep it to a minimum just for the sake of consistency between levels. Similarly, there's the question of consistency between devices. What you're seeing here is our low spec running on the left and our high spec running on the right. And consistency is a factor here. As tempting as it would be to take the color grade on the right there and go all Mad Max Fury Road with it and just paint the whole thing orange and just ramp the contrast up, if we did that, it would create a massive visual disparity. The players would download our game on either device and be like, what the hell is this? 1-star review. And that's not what we want. So from an art direction point of view, we made a decision from the outset that our post effects, and in this case our color grading, has to make the game look better, but it can't make the game look too different. And this actually helped influence how we'd approach this from a code perspective. Realistically, we need to support a color wash, and changes to contrast, and changes to brightness. But it doesn't necessarily have to be an all singing, all dancing color grading workflow to deliver the look we want. So the goal of this, from our perspective, was to, I don't want to say do as little as we have to, but yeah, because there are other post effects that we want to support, and we have finite resources in terms of GPU. So we looked for the most cost-effective method of color grading that we could find. And imagine our surprise when we found that the 1D color ramp that ships with Unity's image effects turned out to be the cheapest solution we found. Instead of storing an uncompressed 256 square lookup table, we can just store a 64 by 1 color grade, and that does pretty much everything we need it to. We can do color washes with it, we can do contrast and levels and brightness, and pretty much anything you can do in Photoshop. The only thing it doesn't give you is saturation. This wasn't necessarily called out in the art direction, but because we're awesome and we over-deliver, we put a saturation in as a slider. So we had that option for art direction, even though it wasn't necessarily required. So that's all I've got with regards to color grading. Let's have some bloom. Make them cars pop a little. And the way we do our bloom is largely quite standard. It's done with a series of blurs. One blur horizontally, one blur vertically, and then we additively apply the result to the screen. And the way we generate those blurs, again, is tried and trusted methods. You'll probably find similar things on Google, but the idea of it is that we take a bunch of samples, multiply our UVs by those samples, read the texture a number of times, and then average the result. So far, so standard. But as you can see, for each blur, we're sampling the texture 11 times, which is scary expensive if we're going to do that at full resolution. So this would be a candidate for rendering in a separate pass at a lower resolution and then putting it on the main scene, which is what we did. And in this case, it proved advantageous because with the bloom effects, and especially with blurs, you get a blurrier result the lower res you go, obviously. And in the case of blooms, it means you get a nicer, softer, wider highlight on things. So we went right down with it and ran at an output resolution of something like 200 in the x-axis, and that gave us the result we wanted. But this isn't a final solution on its own. If we were to take that texture and additively apply it to that texture as is, it looks like a bomb's gone off. It looks a bit late era PS2, we've just discovered bloom and we're going to write our art style around it. That is not the look that we want for CSR2. We want it to look all next gen and HDR looking. And even though we don't necessarily have HDR bloom buffers for this, so I can't say that this white pixel here is X million % brighter than this other white pixel here, we need another approach to get the look we want. So we looked to masking. The idea of being able to turn off the bloom on pixels where we don't want to see it and turn up the bloom on pixels where we do. And to do this, we needed a second render target. We want to be able to take that scene, but only capture the elements that we want bloomed, and then pass that to our bloom shader as a mask. And we were able to do this by exploiting our frame buffer. See, the frame buffer you get with a forward-rendered pass in Unity has 4 channels in it: red, green, blue, and alpha. Red, green, and blue we need, obviously, but the alpha channel in our pipeline is largely vestigial. Our post-effects pipeline doesn't use it at all, but our shaders could use it because we support transparency, but at the same time, because we have control over the blend functions, we don't necessarily have to put transparency in there either, so we've got a free render target. So in this particular shot, and this is a capture from the editor, which is why you've got a camera floating in there, but what we capture in our alpha channel of our frame buffer is the specular contribution of the scene and the emissive contribution of the scene, and optionally also sky visibility, but we can just send that to the bloom shader and literally do a multiply, and that gets us the result we want. So going to a practical example, here is the scene without any bloom on it, and here is the scene with the bloom isolated to just the specular on the car and also the light on the left side of the screen there. If I wanted to also have it affect the sky outside to give the look of exposure adaptation, I can do that too. And this is quite a useful tool because you can start getting creative with things as well. So I've got this foggy, wet weather environment here. If I wanted to do volumetric lighting effects, maybe not light shafts, but sort of in that general direction, all we'd want to do there is to be able to make the bloom more visible the foggier the screen gets. So all we need to do there is mask to the emissive, as before, but then multiply the result by the inverse of the fog distance. Now, because we've got completely custom shaders at this point, we know the fog distance. So for the sake of one extra multiply, we can get some pretty nice results. So one last implementation detail about our bloom pipeline is bloom saturation. As you all know, even with masking, if you start taking textures and additively overlaying them on one another, things turn white very quickly. You can see the sun on the right-hand side of the screen here. It looks bright, it looks bloomy, but it doesn't necessarily look particularly HDR. And comparing it to HDR photography, what we find is that when things are over-brightened, they don't go white, they go heavily saturated, and the white spot is just like a very tight highlight in the center of the bright object. The very tight highlight is beyond the scope of what I'm showing here, but in terms of getting the saturated look, that's easy. We can just literally saturate the bloom pass before we overlay it onto the scene. And it's even easier than that because we wrote a saturation slider for the color grade, so we can just copy and paste that, and that gets us the look we want. So we've got our bloom, we've got our color grading. This is clearly a shot in motion, so let's have some motion blur. And the motion blur was massively opportunistic. It was a feature built entirely from leveraging existing features, in that when we did the bloom, we wrote a horizontal blur as part of that process. CSR2 is a game where the car always travels left to right. We don't steer or turn the cars, and we don't do first-person mode or anything like that. So we don't have to worry about motion vectors or motion direction. We can just do a horizontal blur, and that will give us the look we want. So we just, for our first prototype, we just literally copy-pasted the blur from the bloom pass, overlaid it onto the screen, and that got us a pretty pleasing result. People were getting excited about it. As a prototype, it was great. As a shipping solution, not so much, because we went quite low res with our bloom pass in order to get the nice soft highlights. So we realized that motion blur needed to be its own pass. And with the render texture, we made it taller, but because we always know we're blurring left to right, we don't need to care about horizontal pixel fidelity, so let's keep it narrow. But just like with the bloom, there's control issues here. If I overlay the motion blur texture onto the main scene, the world looks nice, it looks good and fast, but the car looks blurred. The car is the star. We want the car to remain sharp at all times so that the players can see this thing that they spend so much time tuning and customizing and so forth. So we had to go back to the drawing board again. In a perfect world, if we had motion vectors, we could be able to calculate the delta of each pixel on the car per frame to that of the camera, to that of the world, and then blur things accordingly. But we don't have that render target. And even if we did, it would be a tremendous waste of resources given how much we need to achieve and the other features we want to support. So we went back to our old friend masking. And again, this is sort of using an exploit of the art direction. At any point in the game, even when the car is in motion, the player car is always in the center of the screen because the car is the star. So we only need to turn the motion blur off in the middle of the screen. So we create a vignette that masks away the effect of motion blur, so anything in the middle of the screen, in this case the player car, remains sharp while the periphery of the environment remains blurred. I have a video to show what that's doing. So this would be our motion blur effect minus the vignette. The faster you go, the more myopic everything gets and the more blurred it looks. With the vignette enabled, and this is how we released it, the car looks nice and sharp. It gets a bit blurry at the edges, but that just sits it in the world. But the environment looks fast. It looks like you're driving past it. If I turn off the main scene and just show the motion blur contribution, this is what the vignette is doing. And final implementation, and this is just another purely opportunistic feature that we just repurposed from what we'd written before, was the vignette itself. We've got this system where we wrote this code-based vignette system for the motion blur, but why don't we just render it on the screen as well? As in, just invert it, color it in, stick it on the scene, and just get nice, soft, dark edges around the corners. And we did that, and it was quite nice. It wasn't initially part of the art direction, but at this point it's performance-free, because we got to do it anyway. And it does draw the player's eye to the center of the screen where the car always is, so it just proved to be a win on all grounds. So, at this point, we're pretty much a mature post-effects pipeline, at least by our standards at this point. And there was one more thing we wanted to add, and that was full-screen lens effects. The original brief for this effect was to do lens dirt. So when the light is pointing directly at the camera, we want to be able to see fingerprints and smudges all over the screen to give the illusion that the camera and therefore the player are a physical presence in the world. But when you can do things like that, you're effectively asking to be able to draw additive textures based on which way the sun is facing. And that opens up the possibility for full-screen sun flares, or for full-screen lens effects, or for fake light shafts, and all manner of things that look like things you shouldn't be able to do on mobile, but totally can. As an example, this is what the shot looks like with a full-screen lens flare. And the approach for how to do this is really easy. As in, you just take a texture, additively apply it to the main scene, and then congratulate yourself on a job well done. However, this wouldn't be the final implementation on its own. It's not taking sun visibility into account. And in order to do that, you need to know which way is the sunlight facing relative to my camera, and also, is the light currently occluded by anything? Am I inside a tunnel, or am I in front of a large building, for example? And because all of our lighting is pre-baked through light maps and cube maps, this information is not necessarily easy to come by. Luckily for us, we have information that's similar to what we need that was enough to deliver the result, based on things we'd written earlier in previous pipelines. For example, even though our cube maps are entirely pre-baked, we do support a real-time specular light from the sun for the purpose of ensuring that the sunlight is always the hottest, brightest thing in the scene, regardless of what's been authored. So that means we have what is effectively a real-time key light. So we can do a dot product from this light direction and the camera, and that gives us the ability to turn our lens effects up and down or on and off, depending on what that number is. It doesn't give us light occlusion, though. I mean, I'm busily playing with the lens flare here, and you can see it drawing inside the object like that. And that's the thing we also need to solve. We need to solve the occlusion problem so that we know when we're in tunnels and what have you. But even that's pretty straightforward. So I've got a debug view of our race here, where there are trigger boxes that have been painted blue. And the purpose of these trigger boxes is that they control the shadow intensity on the cars. So when a car drives through a light-mapped shadow on the ground, it appears to get darker because the trigger box is saying, multiply the reflections on the car by this number. But the thing is, this number is effectively an occlusion pass, because when a car is in shadow, it stands to reason that the key light is being occluded by the environment. So we can multiply whatever this number is at any given time by our lens effect, and then we can turn the feature up and down and on and off as we need to. So putting all of that into practice, here's our full screen lens flare again, and you should see it switch on and off as the player drives in and out of the buildings. And not only does it add a degree of realism, but it also gives us a degree of sense of speed that we previously didn't have at all, because we can just dapple that effect on and off as it drives through overpasses and the like. One last implementation detail with regards to full-screen lens effects is aspect ratios. Because iPhones and all Android devices, 16:9, but iPads are 4:3. So if your full-screen lens pass requires a certain aspect ratio to look a certain way, your texture is going to get squished. Fortunately, this is an easy thing to compensate for. And the code for it is pretty straightforward too. You only need to know two things. The camera aspect ratio relative to 16:9, presuming that 16:9 is the widest aspect ratio that you wish to support. And you also need to know an offset from the center to the edge of your screen. And then just using a very, very simple bit of math that you can put into your vertex shader, you can pass that to your lens effect and scale it accordingly. So, rewinding a bit and putting all of that together to recap, this is how we started. And this is what we released with. It's a pretty big change, and it's a very good polishing step. But there is always room to grow. And part of what I'm showing here is as much to hopefully inspire as it is to inform, because everything we've written here is designed to run 3 to 7 millis on an iPhone 6. But of course, iPad Pro's out, iPhone 7's out, iPhone 8, 9, and 10 are going to come in the near future as well. And we're always going to have room to grow. We're lucky in mobile because every year it's the equivalent of another console generation. As long as there is the will to improve and the will to move the graphics, even after you've launched the game, you can do pretty much anything you like. Case in point, with this shot here, we can see there's room for improvement. The car looks like it's moving, but at the same time, the wheels aren't blurring, so it does kind of look like the car is static in a world that's flying beyond it. We had wheel blurs in soft launch, but for app size reasons, we had to take them out. It's something we're looking to put back in. And that's the sort of things we're thinking of. And there are other ideas for the future as well. But anyway, let's get on to some conclusions. And I have two of these. The first one being, you want to pick your battles. At any one time, you're never trying to write the world's greatest motion blur system or the world's greatest color grading system, because God knows we did neither. The purpose of it is to deliver an art direction. There is a brief, there is a visual target, there is a concept image or whatever, that once it looks like that, you're golden, you're ready to release. And when you've got that kind of perspective, it gives you the ability to make judgment calls on things. You know, how much time / resources / GPU do I want to spend on this one feature when measured against the rest of them? And when you have that, development just becomes a lot easier. Second point in my conclusion, you want to be able to repurpose any existing tech in order to create new stuff. Our motion blur was a prime example of this. Similarly, the bloom saturation and most of the lens effect stuff only worked because of things we'd previously written before. And to an extent, this is helpful, but it's also lazy in all the ways that you want to be lazy, because it means that not only do you not have to write new things, but it's easier to bug fix, it's easier to optimize, it's easier to document, and your artists already have exposure to it, so it's very simple to create things, and it's just good for your own sanity as engineers. So, obligatory we're hiring slide, because of course we are. If you saw anything you like the look of and you'd wish to be a part of it, you know, give us a call, give us a bell. I've got both mine and Liam's contact information on there. We can pass on any inquiries you may have, and while we do so, we'll collect those sweet, sweet referral bonuses at the same time. We can help each other out is what I'm trying to say here, you know. But other than that, do we have any questions? Hello.
Obviously, you guys worked linearly for your, first off, a PBR system inside Unity 4.
Thank you, thank you. Oh, hang on.
That predates Unity.
Oh, yeah, please.
Obviously, work in a PBR workflow for the car. What do you guys do for the environments? The performance for iPhone are usually pretty small. So do you guys still use your PBR systems on the environments?
Just to repeat the question, just in case it doesn't come out on the mic, it's you're asking about what do we do on environments with regards to physically based shading, yeah? Well, we use the same system, so we scale it a lot quicker than we do on cars. Again, this might be going a little bit beyond the scope of what we're showing here. We've done it in other conferences in the past, but in the environments, on the high-spec devices, we have everything, the physically based specular and all the rest of it. And then by the time we get to, say, iPhone 5 or mid-spec Android, you know, we turn some of it off, and then by the time we're on low spec, we've turned all of it off. And it's just a balancing act to maintain the quality.
I think it's worth mentioning as well that the car shaders are very, very expensive, so the environment shaders are a cheaper version of those, but we are essentially doing very similar things.
Yeah. Any others? Oh, hello.
Thank you, awesome talk.
Oh, thank you.
I'm curious, with supporting so many different devices, what was your process like for figuring out A, what your ranges are? You talked about like having 4 ranges, and B, kind of keeping on testing regularly as you went through your process.
Yeah, sure. I mean, as I said, alluded to in my talk, is we started off in soft launch with 80 different devices. And there was a plan over the course of soft launch to hard launch to increase that, particularly on the Android range, which is where most of the big devices are, but also in the sort of bottom range of iOS, because I think we were limited to iPhone 5S, but then we dropped down all the way to like 4S and iPad Mini 1. And part of that, yeah, we've got in previous talks from GDC much more details in the scalability challenges that we had there of breaking into different shader LODs, different geometry LODs and whatnot. But yeah, I mean, we've been building a sort of an improved pipeline of QA testing and performance, results and whatnot. We'd love to have something like Inside was like what they showed you last night. But yeah, that's something we're moving towards, because you get content changes all the time from the regular release schedule, and it can affect certain portions of the devices, particularly your mid-end, maybe the bottom end. It varies from time to time, and we get like I think it's about like bi-weekly reports back of saying that these are where the performance have been shifted and whatnot, and we can address those problem areas.
Yeah. From a practical perspective, when you're first setting that up, in the case of iPhone, just have one of every device you're going to support and just run the game on it, and then set which shader loads you think are going to work and which post-effect settings you think are going to work, and then that broadly defines your specs. In the case of Android, it's better to categorize things based on which GPUs they're using. So you might have a different thing for Adrenos or a different thing for Snapdragons and things like that. And then once you've got those figured out, you don't necessarily need to test every device in the spectrum, because that would just be overkill and a QA nightmare. So you just have a representative from each spec. So you have one device that's going to be your benchmark for high end, and one for your low end, and one for your middle, and just keep an eye on those whenever any new features go in.
Thank you.
Thank you.
I was curious about your anti-aliasing. Do you have any other method besides the MIP bias that you use at runtime? Or is that pretty much solely it? I imagine the speed kind of helps with it, but...
Yeah, I mean, we have a very long list of features that we aim to implement, and the device scalability problems are, there's huge number of different devices from all the way through the top to the bottom end. So we don't actually support anti-aliasing at the moment, but certainly with all the new devices coming to the market, we're very keen to add those features and whatnot, particularly with our migration to Unity 5, which is going to give us quite a big perf gain.
Awesome, thanks.
Yeah. Oh, I think we've got someone patiently waiting.
Thanks. First of all, amazing job. Like, what a big difference from the before and after, and all the attention to details that you guys put into it. It's amazing and inspirational. I had a question. You kind of answered it about we have a problem with QA, right? All those devices, like you said, Android has 2,000 on iOS. It's much more sane at 24 or whatever.
Yeah.
But still. So obviously, like you said, you don't buy all those devices. You should kind of select, like we say, okay, Samsung 4 for this, whatever. But sometimes we run into oddities where, it's always like a Sony Xperia or something, where something's rendering weird. Have you had that kind of experience with your team? And can you talk a little bit about how you solved it, or did you just ignore it and say, sorry, buddy?
Yeah, you get problem devices. A lot of our graphics team spend time on working individual problems. I mean, for example, we do our bone skinning algorithms that we use. We do the multiply over matrices, but certain devices don't support that for some reason. So we've actually had to make a secondary implementation which does a by vector, which is slower, but we need to turn that on those problem devices, because otherwise you get just wheels just fly off all over the poly mesh, and it's just a nightmare. But as I said, our graphics team have been really focused on, you get reports back from the live builds, from the QA and whatnot, there where you've got these strange devices doing odd things on particular operating systems. So then we load those up, debug those, and work on that. I think there's a lot to do with the percentage of. You've obviously got to pick your battles as well. So, if there's like a 0.1% of the user base or whatnot, you can prioritize higher issues of, say, 1 or 2% of those visual issues.
Okay, so I guess that's us then. Thank you.
Thank you.